Okay, let's continue. So I'm going to give you another example to tell the difference between the maximal matching and the maximum matching, right? So let me give you another example of the graph. So this is a graph, what I'm considering, right? And now if I look at this, say, edge A and edge, two edge AB, I claim this is a maximal. Okay, so if you look at this two edge, and you will not be able to add any edge into this set to still keep that set is going to be independent, right? So because if you're adding any more edge into this set, actually any more edge, right? So any other edge actually shares a common endpoint, common vertices with A and B, right? So therefore this is maximal. You see, if you add this one, it has the same vertex here. This one same vertex. This one has same vertex, and this edge has the same vertex, right? If you look at everyone here, so therefore this is a maximal. It's not containing any larger, strictly larger independent set. That's a maximum. If I look at the same graph, by this time, I'm going to use the following edge C, D, E. Right. So this is. I'm still having the same graph, but this time I'm looking at the C, D, E. And now you see I claim this is also maximal. It's independent, and therefore it's a maximal, right? It's a matching, right? It's a matching. You see two endpoints, two vertices, paired. It's a pair. That's a match. That's a match, and that's a match, right? And I claim this is going to be my. This is going to be my. Again, that's going to be my my maximal. And independent. If you try to add any more edge into this set, it will no longer be an independent set, right? So therefore, this is again that's a maximal. As you can see, if I compute my alpha prime G, so that's a cardinality, right? So that's a cardinality of the, if you look at all of the maximal sets, maximal independent sets, that's the largest cardinality. In this case, the largest cardinality is equal to 3. Why? The idea is quite simple. So G is a graph of order n. Right? Order n, so which means if G is a vertex and edge, so which means the cardinality of vertex is equal to n. Right? And assume I have m, so which is the maximum. A maximal matching. So assume this is going to be a maximal matching. In this case, cardinality of M is equal to alpha prime of G, right? So not only it's maximal. Among all of the maximal ones, it has the largest cardinality. But if I look at this matching, basically M is a bunch of edges, A1, A2, say EM, right? So a bunch of edges. And for each edge, you have two vertices. So for each edge, you have two vertices. Because any two edge shares no vertices, right? All of these two vertices are different. Now let me look at all of the vertices covered by this M, right? So then I see the total number of the vertices covered by this M is exactly equal to, so vertices covered by M. If I look at vertices, if I look at vertices covered by M and I count the number of these vertices covered by this M is exactly equal to 2 times the cardinality of M, right? Because each edge covers 2 vertices, and I have this many, so therefore this is equal to 2 times alpha prime of G. But of course, the total number of vertices should be less than or equal to M, right? So a quick corollary is 2 times alpha prime of G should less than or equal to N, and in this case, less than or equal to N over 2. But sometimes N over 2 might not be an integer, so I'm going to look at the integer part. So that's a low floor there, N over 2. So this is the integer part of this quantity, right? Integer part of this quantity. So alpha M is always less than equal to N over 2, right? So that's a proposition we can propose. G is a graph of order n, then alpha prime of G. So that's is always less than equal to N over 2, the integer part. The integer part of N over 2, right? So now if I come back to here, let me count how many vertices I have. 1, 2, 3, 4, 5, 6, 7. Right? So I have 7 over 2. That's 3.5. The integer part is equal to 3, right? So that's exactly equal to 3. Okay, so this means this matching actually is a maximum, right? So there's no way to be a cardinality to be larger than 3. So therefore this one is a maximum. Not only it's maximal, but it is also maximum, right? Okay, so an easy way to tell a matching is maximum. So basically is you can use this inequality, right? But a lot of times, let me give you another example. Say I have this is a vertices. That's a graph of G. Cardinality of G is equal to 1, 2, 3, 4, 5, 6, 7, 8. 8. And I claim if I look at this edge, if I denote this A, denote this this B, AB is a maximal. I will not be able to add any more edge into this set to still keep the independent, right? So this is maximal. This is M1 and M2. I'm going to find another one. I still have A here, but this time I'm going to have a C here, and then I add one more edge, D. A, C, D. So I have this edge, and then I have here. So I have these 3 edges, and again you can easily check this is this is a maximal, but I claim this one actually is a maximal. Not only it is a maximal, but also it is a maximal. In this case, you see the cardinality of M2 is equal to 3, right? And a half of the cardinality of the order is equal to 4. And I cannot use the result to claim this is a maximum, right? So I do have to use some other other result to verify actually this is a maximum. So that's the next result I'm going to introduce. So let me just record some of the basic concepts, right? So a vertex is covered by a matching M, right? So if the vertex is an endpoint or is incident to an edge in M, right? So that's an edge in M. So that's the endpoint of some edge. It's an endpoint of some edge in M. So that's what we covered. A vertex is called free if the vertex, if it's not a covered vertex. So a vertex is free, so which means it's not an endpoint. Endpoint of any edge in the matching, right? So that's what we call the free. And I also want to introduce an M argument. N argumented path. An M argumented path is a path if I denote a path, so then this is say V1, and then they'll go to V2, go to V3, right? So go to V4, and so on and so forth. Go to Vk. A path, so which means this is edge 1, this is edge 2, right? Edge 3, and this is edge k minus 1. And a path, so which means all of the edges are different, right? So a path means all EIs are distinct. So that's a path. So they might among all of this vertices, the vertices can be the same, but all of the edge is going to be different. That's what we call the path. And satisfying the following properties. So suppose this is a path, and then with the following properties. First one is V1 and Vk are free. Right? So which means they are not adjacent. They are not adjacent to any edge in the graph. And the second one. So I wanna E1 is not in M, but I want E2 is in M, and E3 is not in M. I want E4 is in M, and so on and so forth, right? So which means the property of what we can call it's alternating. Okay, so it has second property is I want all of the even numbers are going to be M, right? So this is not in, not in, not in, not in, right? So that's what we want. This is what we call the augmented path. So it starts with some free vertex, because from a free vertex go to M, right? So E1 apparently cannot be in, right? Then I'm going to ask the next one is going to be in, and the third one is not in, fourth one in. That's alternating, right? So with these two conditions, so this is what we call M argumented path. There's one property what we can prove. That's what we call the Burgers theory. Which says a matching M is a maximum if and only if and only if there's no M argumented path in G. So there's what we call the Burgers theorem, which tells us how we can tell a matching is going to be a maximum. Right? It's not only maximal, it is also maximum. So what if and only if there exists no M argumented path in G. Okay, so before we present the proof, maybe I just sketch an idea how we are able to prove this result. And let's come back to this example. And why the first one is not a maximum? The reason is if I look at the first one, I can examine the following paths. I claim this is an M argumented path. I claim this is remember this is this time I only consider A and B, right? So you should ignore this C and D. So if you look at this path, right, it starts with here is my matching A and B. This is going to be my matching, right? So that's maximum matching, and then I claim actually I will be able to find M argumented path because these two edges are free. These two vertex are free vertices, right? So they are not incident to any edge in the. They are not edge covered by this matching. And I start from here, right? So this one is out, and then this is in, and then out. Now you see this is an M argumented path, right? There exists an M argumented path, so therefore this is not a maximal one. Because the reason is quite simple. What I want to do is for this one, suppose there exists such path, right? So I'm going to replace this path by this edge B, by this two new edge, right? So this is, say, I'm going to call this B1, this is B2. Then together with the original one, so if I consider from here, I consider another one, say together with the original one. B1, B2, then I'm able to obtain another maximum matching, but with a larger cardinality, right? So therefore this one is maximal, but not a maximum, because if I look at the path, I'm going to replace the one in the path by the one outside the path. But if you look at our definition, right? So this one's in, out, right? So the total length for this path has to be odd. So length has to be odd. Right? And the one in M is an even number. So which means that one outside of M is going to be odd number. The odd number is strictly larger than this even number by 1. So what you need to do is replace the ones in M by the ones not in M. Right? And you are able still will be able to obtain another matching, and which has a cardinality strictly larger than 1. Right? So that's a reason why you can prove this result. why you can produce blah. So in case you are able to find an m argumented path, then you look at your path. Start with two free vertices, right? And this one is out, in, out, in, out, in, and the last one has to be out, right? So therefore, the total length of this path has to be an odd number, and the ones in M has to be even number, right? And what you need to do is replace these even numbers by the odd numbers. If you replace these even numbers by odd numbers, right? And with the ones not on this path, together with the ones not on this path, you are able to obtain another matching which has a strictly larger than 1 cardinality, right? So therefore, if there exists an augmented path, then this one has to be a maximum, right? If there exists an augmented path, and one cannot be a maximum, right? So this is easy way you can do that, and with a little bit of careful analysis, and use this idea, and you will see that you will be able to prove this result. Okay, so that's how we are able to tell a matching is a maximum. So which means easy corollary, right? An easy way to tell a matching is maximum. So if and only if you are not able to find an m augmented path, right? So let's come back to this original example, and my original example says I have and I claim A, C, D, right? So this is A, this is C, this is D. So these three edges. My second one, M2, is A, C, D. I claim this is maximum. The reason is what you need to do is check for a free vertex. Right? So you only have 2 free vertex here, either here or here. So if you are able, all you need to do is check whether you will be able to find m augmented path. Right? So now you start with here. So you go inside, and because it's alternating, right? So therefore, the only way you can go is you can alternating. Not in, and you have to move in, right? But here you reach the end point. There's no way to form an m augmented path because you stop here, right? The same reason, if you start with this vertex, go out. This is not in, and the next one you have to be in, right? Again, you have to go on this edge, and then you stop here. You cannot continue, right? So therefore, there's no m augmented path in this for this M2. For this M2, there's no augmented path, right? So therefore, this is a maximum. So that's once you know this result, and then this is very easy to see. Although I know the cardinality is equal to 3, but I know this is a maximum one, right? So that's how we are able to tell a matching is going to be a maximum. Okay, so now let's come back and discuss a little bit more on this alpha prime of G, right? So this is equal to the cardinality of the maximum matching. So what I'm interested, of course, is try to find what's a value for this number. So we start with some easy examples, some standard one. The easiest example of the graph is a circle, right? So if G is a circle, Cn, so that's going to be and alpha prime of G. Of course, if I start from here, it's in, out, in, out, in, out, in, out, right? So, but anyway, if it is even number, then this is if this is in, and you can match this to be out, right? Not in, not in. So therefore, this is going to be n over 2 if n is even. But what if n is odd? Then if you assign alternatively, right? In, out, in, out, in, out. The last one you can assign is in, but this is going to give you a contradiction. You cannot assign two ins, right? For two ins because they are going to share the same vertex. So therefore, there's no way you can assign assign this edge. So therefore, this in, out, and then you stop. So that therefore you count how many edge in the matching basically is the integer part of n over 2, right? Because a number should not be larger than that part. So therefore, in this case, this is exactly equal to n over 2, the integer part. So that way is easy. The second one. If G is equal to the complete graph. So if I have a complete graph, say I have a complete graph, right? So in this case, alpha prime of G is equal to 1 because you are unable to find the one edge, right? And if you add, is it 1? This is not a 1. Oh, that's not correct. I have to be a little bit careful. This is not correct. The one actually we can consider is G is bipartite KRS. That's a perfect fine. So this is a bipartite graph. So which means you can cut this into vertex. You can cut it into these two sets, U and V. This is U, and this is V, right? And it's complete, so right. So therefore, everyone is joined. Everyone is joined. And in this case, the I prime, the matching is everyone is matched to someone there, right? So that's the smallest number of R and S. Here, the cardinality of U is equal to R. The cardinality of V is equal to S. So that's equal to the smallest number of between R and S, because anyone can match to someone here, right? So it's a complete. So there's the easy way you can do that. What if the graph is not is not complete? So one special case what we're going to consider is for any bipartite graph. So say the third one, G is bipartite. So in this case, G is equal to V and E with you can divide V into two sets, right? U union with W, such that U intersect with W is empty, and edge and edge in E has one endpoint in U, and the other one in W, because the edge really joins one point in U and to another point in V in W, right? So that's what we call the bipartite graph. So bipartite graph, right? So here, most of our problem come from the reality, right? So these are the number of the people, these are the jobs, right? So most of these examples are by graph. So what we are interested in is try to find alpha prime of G is equal to this what value. More specifically, if you multiply by that example, the thing what we interested is when alpha prime G is equal to the if in a complete one, right? So that's a smaller cardinality between these two partitions. So therefore, it will still be true. It's a minimum of cardinality of U and with cardinality of W. Okay, so now the question is when alpha prime is equal to the minimum, right? So basically what it means is if I have, say, 3 people here, if I have 4 jobs there, so if I'm able to find such matching, right? So such that alpha prime is exactly equal to smaller one is equal to 3. So which means everyone is assigned 1 job, right? So when I can have this equation. So this is what we call the host condition. Let's look at in order to study this problem, we are going to introduce what we call the host condition. So what do I mean host condition? So say let X be a vertex in a graph, and I'm going to define the neighborhood of X, which I'm going to denote this by which is denoted by neighborhood X, right, to be the set of vertices that the set of I can just say adjacent vertices that are adjacent to X. So that neighborhood basically is if you look at say a graph here, this is V1, V2, V3, V4, and the neighborhood of V1 is look at all of the vertices which is adjacent to V1, right? So which is V2 and V3. Notice V1 is not in the neighborhood, because neighborhood just means neighbors, but does not contain cell. So that's a vertex. So say for example, neighborhood of V4. Again, this is a V2 and a V3. Right. So they are the neighbors. They are the neighbors of V4. And let say S is a subset of the vertices. We define the neighborhood of S to be neighborhood of S is equal to you consider all of the vertices in S, and then consider union, right? So you just put them together, right? So you just put them together. So S is neighborhood of S is you consider for each vertex you consider neighborhood, and then you consider union. So for example, if I have V1, V2, V3, V4, and if S is equal to V1, V2, Right? So what is the neighborhood of S? Neighborhood of S is neighborhood of V1, so which is V2, V3, union with neighborhood of V2, right? So which is V1, V2, V1, V4. So therefore, the neighborhood is V1, V2, V3, V4. Right? So that's a neighborhood, neighborhood of S. Right? Okay, so I think this is relatively easy to understand. Okay, so now once I have this concept, now let's come back to the bipartite graph. So suppose I have a bipartite graph. Right? So suppose I have U here. Suppose I have V here. So you have a few of edges. Right? So now, if you look at, assume there exists a matching M such that the cardinality of M is exactly equal to, here if I assume the cardinality U is less than equal to W. So if I know there exists a matching such that the cardinality matching is exactly equal to the number of U. So what does that mean? So which means everyone is paired with someone from W. Right? Everyone here is paired with someone in W. Of course, W, the cardinality might be larger, right? So you might have this one. So for example, this is matched to this point, and this is V1, U1, U2, U3, W1, W2, W3, W4. Right? So I can pair the U1 with W1, U2 with W2, and the U3 paired with W3. Right? So that's a matching. Everyone is paired with someone, some distinct one from W. If you assume there exists a matching, then in the language of this neighborhood, I can claim is for every subset contained in U, which is not equal to empty, I should have the neighborhood of S. So the ones in W, the cardinality should be larger than equal to the cardinality of S. Right? Because everyone, right, so is matched with someone from W. So if you look at any subset, if you just look at any subset, right, and because everyone is matched, so which means that once you match is in the neighborhood. Right? So if you consider, say, if this is your S, right, and apparently the one you match, of course, belong to the neighborhood of S. Right? So the cardinality of the neighborhood of S apparently should be larger than equal to the cardinality of original S. Right? So assume there exists such matching, such that cardinality M is exactly equal to the cardinality U, then everyone is matched with someone from W. Then given any subset, you will be able to see the one you match, of course, belong to the neighborhood of S, right? So there's one-to-one corresponding from there. So the neighborhood of S might be a little bit larger. So therefore, you should have this condition. Surprisingly, the converse is also going to be true. So that's what we call the Hall theory, which says let G be a bipartite graph with the vertices of G can be partitioned in two sets, right? So let me say that you have two parties, U and W, such that cardinality U is less than or equal to the cardinality W. And let me denote the cardinality U by R. then f of G, the independent number of vertices for the graph of G, so which is equal to R, which is equal to the cardinality of U, if and only if here I assume if there exists a matching such that they have the same cardinality, then I have this condition, right? So the converse is also going to be true. So which means the neighborhood of S, the cardinality of neighborhood of S is always larger than or equal to the cardinality of S for every non-empty set S which is contained in U. So the converse is also going to be true. That's what we call the Hall theory. So as I explained, this way is easy. This way is easy because if you assume there's a match, right? So for any subset, if you look at the neighborhood of this subset, because there's a matching, so the one you paired, of course, is contained in N of S, right? So the cardinality of this number, of course, is going to be larger than or equal to S. So that this direction is easy. So the converse direction, right? So the opposite direction is a little bit hard. So let me just briefly mention how we are able to prove this result. So we are going to prove this result by using. So suppose I know this is true. Suppose I know this is true, and how I'm able to know that the alpha prime of G is exactly equal to R, right? So let's look at how we are able to prove it. We are going to do a proof by induction. On R. So the proof by induction on R. So if you do a proof by induction, so let me assume step 1, right? So let R is equal to 1. Then in this case, this is easy because you only have one vertex, right? So that's in your U. And W, you have quite a few of them. But I know the neighborhood from this condition. If you look at just the neighborhood of U, the cardinality should be larger than or equal to the cardinality of U is equal to 1, right? So you will be able to, the neighborhood, there are at least one element, this is U here, there are at least one element W here, right? So now you will be able to find a match U to W, right? So that's easy. So this is easy. So step number 2. I'm going to assume the result is going to be true for arbitrary k, right? I want to prove for arbitrary k plus 1. So let me use, say, a little bit different. Let k larger than or equal to 2 be an integer. So assume the result is true for any R which is less than or equal to k minus 1. So my language is, say, suppose I already know the result for k minus 1, and then I want to push what I can know on k, right? So that's the reason I say start with k is larger than or equal to 2, because when k equal to 2, the result has already been known when k equal to 1, right? K minus 1 becomes 1, right? So now we want to know the result is true for R equal to k. So that's what we want to consider. Whether the result is going to be true is a question mark. Whether the result is going to be true when R is equal to k minus 1. So now let me assume let G be a bipartite graph, and with two sets, U and W, such that the cardinality of U is equal to K, which is less than or equal to the cardinality of W, right? And also it satisfies this Hall's condition. for every non-empty subset, you should have non-empty subset. You should have a cardinality of the neighborhood of S is larger than or equal to cardinality of cardinality of S. So I'm going to put it into consider two cases. Case number one. So if I assume the following is going to be true. Assume for every S in U, I have if the cardinality of S is larger or equal to 1, strictly less than cardinal of U, so in this case it's K, implies is strictly larger than S. Right? So here my condition says larger than or equal to. Right? So what if I know this for everyone? I know this is strictly larger than. Right? So that's a little bit stronger assumption. So I know for everyone that the cardinality of the neighborhood is going to be strictly larger than. And I'm going to prove this with a little bit stronger assumption and prove the result. So therefore, if I just pick arbitrary elements in U, then I know the neighborhood of U, the cardinality, is larger than equal to 2. Right? Because it's going to be strictly larger than 1, and therefore this is larger than equal to 2. And it's larger than equal to 2, so there exists a W in W such that UV, UW are adjacent. So you have a bunch of them. So you have this is your U, this is your W. You just pick one point, right? So it's paired with W here. Now you consider